Now, a fracture has multiple parts as you look at it on a large scale, and a few different forms that it can take. You can have large, vaguely circular, coin-shaped fractures that are expanding basically in all directions radially, but in a plane, so not in a spherical sense, but just expanding along all of its edges in a circular manner, where it intercepts the surface of the ground if it reaches the ground. Obviously, the fracture will not extend into the air, so then you just have a fracture trace on the ground. Fracture tips are the edge of that fracture trace where it dips into the ground, and you have the fracture front, the leading edge of the crack. If you have a buried bed, like in this bottom image here, it may have started out as fairly coin-shaped, but once it reaches the top and bottom of that bed, it doesn't extend. If the beds above them are different materials, which is reasonably implied by them being a different bed, that discontinuity there ends the crack. So the fracture extends sideways out into the bed and starts becoming blade-shaped. So to kind of step back again a little bit, what is it? I said it breaks into different pieces, not recoverable. Going down to an atomic scale using little balls and springs to represent atoms and atomic bonds, they have a preferred orientation. If we stress them and the bonds can handle it, we have elastic deformation, like in the center here. If the stress was removed, they could return to their favored condition, which is shown in part A. If we stress them too much, and those bonds, or those springs, can't handle it, they'll break. Other parts of it will return to normal, but you'll have two separate pieces. So the fracture relieves the stress. The bottom half of that spring ball structure is no longer stretched. The stress is gone. But you have two distinct pieces. The fact that the stress is gone after the fracture is very important. That comes up in more circles. It comes up in many places in lab and in lecture, and just in conceptually thinking about the formation of structures. Now, we can get fractures in two different ways when we apply compressive stress. So up in part A here, we're primarily pushing vertically, just up and down pressure on this block, with a little tiny bit of confining pressure from the sides. We can get a joint where we actually get a tension crack. This can seem counterintuitive at first, but think about if you've ever taken a paperback book, put one hand on the spine and one hand opposite the spine and push together. The book bulges in the center, and at some random page, half the book is bulging to one side and half the book is bulging the other way, and you have a gap in the middle. That's a tension crack caused because as things start flexing to try to deal with that stress that you're applying, it's bulging, some to the left, some to the right. In the center, there's tension. It's just like grabbing the left and the right and pulling on them. The other way that it can break is getting a shear fracture. the shear fracture at some angle, we'll discuss what angles later, where now if you're pushing on the top and the bottom, those two blocks could slide and relieve the pressure. And even in each of those different cracking cases, there's two ways that it can happen. You can have straight up frictional sliding. In the joint, this will only happen if then you apply new stress in a different direction later. So we had vertical stress creates the crack, then we go and we push on two opposite corners. Now it'll slide past each other, and that'll be frictional sliding. Also, if the crack is kind of, not a nice straight line crack, or as it starts sliding and grinding, it starts breaking off pieces. As it moves further, we get cataclastic sliding. This is sort of like if you take a heavy box and you set it on the floor and you try sliding it by pushing or pulling. That's like image D. If instead you lay out a whole bunch of marbles on the floor, set your box on the marbles, and then try pushing or pulling it, that's like cataclastic sliding. Much easier because all of those marbles are rolling. There are like little tiny wheels in there, and cataclastic sliding happens much, much more easily, takes less stress than frictional sliding. Now, in the case of C, the shear fracture, if there's a nice clean break, we can get frictional sliding. So we push down on the top and up on the bottom, and they slide. Relieves the stress, they move. We have a shear fracture or a microfault. If on the other hand, the break isn't very clean and it starts grinding and creating loose pebbles and stuff, now we can get cataclastic sliding. Also, in this case, called cataclastic flow in a shear zone. Once again, takes less stress to move it if you've got this cataclastic material in there. Now, there is a paradox. Rocks are breaking all the time. Buildings, bridges, mountains, lots of different things made of rock and or cement break. And they break with a lot less stress than they should. Precisely 10 times less stress than they should. These things should be 10 times stronger than they really are. So why? Well, the answer is Griffith cracks, named for the guy who discovered them. Griffith found that even in something that doesn't look broken whatsoever, and therefore should be incredibly strong, there are tiny imperfections, tiny cracks that we can't see. They weaken it. So every substance has microcracks along which the material could fail, and we now call them Griffith cracks. It could be down at the atomic level. This crack is 5 atomic bonds long. Something happened, they didn't bond quite right. It's a weakness. That weakness can grow when you apply stress. It's like taking a piece of paper. If you take a sheet of paper, nice, you pull it right out of your printer, tug on the sides. If you're tugging fairly evenly, kind of like in the little cartoon here, the paper's fairly sturdy. It's fairly strong. If you take scissors or just your hands and create some starter cracks, and then you tug on the paper, it can rip in half very easily. And the bigger the starter crack you give it, the more easily it rips. We'll go into the exact details, about that later, or if you want lots of details on that, geophysics gives you precise equations on exactly how the crack size affects the stress needed and everything like that. It's actually pretty cool, I think. Hopefully you think so too. Now, we can get cracks by having actual tension, an overhang on a cliff. The underside of that overhang is being pulled by gravity. It's attached to the rest of the cliff, so there's tension. Or, if we have a lamp hanging from our ceiling, there's tension. Whatever the material, if there's tension, this is what's going on if there's failure. So if we have a cylinder or anything and we have tension on it and minimal confining pressure, some of the micro cracks will open up because you're tugging on it, and the tips of the cracks will start extending, kind of like in that paper. As you tugged on it, the rip extended from the tip of the rip or the cut. And a fracture is created typically very close to perpendicular or precisely perpendicular to that tugging. As you tugged on that paper, it didn't create a rip at some angle. It created a rip straight down, perpendicular to how you were pulling on it. So what happens is, as it's tugging, the cracks are kind of opening up, and they're not flat anymore, they're kind of bowing. And whatever crack happens to be the biggest one perpendicular to that tension grows the most. The larger it grows, the faster it starts growing, until it completely splits the rock in half. It has failed, it has fractured. It relieves all of that tension stress, so the other cracks close up, they're tight, they're no longer bowing. And we call this one that broke all the way through a through-going crack. Straightforward name. Nobody got creative and called it, a Freddy crack or anything like that. It's a nice, through-going cracks go through the rock. So here's a little bigger image so you can see it better.